Hello, and welcome to this lesson on explaining chemical behavior using the Reactivity Series. In today's lesson, we will start off by understanding how the reactivity of metals influences various chemical changes observed in everyday life. We will then learn to apply knowledge of the Reactivity Series to predict and explain the outcomes of specific metal reactions. So far, you've been introduced to the Reactivity Series, a crucial tool for predicting how different metals will react in various circumstances. You've learned the order of metals from most reactive to least reactive. In this lesson, we will utilize this knowledge to explain various real-world observations. To illustrate the impact of reactivity, let us take a look at a few real-world scenarios. Rusting is a common chemical reaction that showcases the reactivity of metals. It is a chemical reaction that occurs when iron reacts with oxygen and water, leading to the formation of iron oxide, commonly known as rust. This process can weaken structures and cause significant damage over time. You may wonder why iron rusts but not a metal like gold or silver. To understand why, we need to look at the reactivity series. Iron is relatively high in the reactivity series, meaning it readily reacts with oxygen and water in the environment. This high reactivity is why iron easily forms rust when exposed to air and moisture. Gold, on the other hand, is much lower in the reactivity series. It is one of the least reactive metals, which is why it does not easily react with oxygen or water. This low reactivity makes gold highly resistant to corrosion and tarnishing. Understanding the reactivity series helps us make informed decisions about the materials we use in different environments. For instance, in construction, materials like stainless steel, an alloy containing iron, but also elements like chromium and nickel to prevent rusting, are preferred over pure iron for structures exposed to the elements. In electronics, gold is used for connectors and contacts because it doesn't corrode, ensuring reliable performance. Another important application of the reactivity series is in the extraction of metals from their ores. The position of a metal in the reactivity series determines how it can be extracted. Metals that are less reactive than carbon can be extracted from their ores by using carbon in a process called reduction. For example, iron is extracted from its ore, hematite, iron oxide, using carbon. This works because carbon is more reactive than iron and can displace it from its compound. This reaction occurs in a blast furnace. This reaction highlights the reactivity principle. A more reactive element, carbon, displaces a less reactive element, iron, from its compound. This method is widely used in the extraction of several metals, making it an essential part of industrial metallurgy. The reactivity series also helps us understand how salts are formed during chemical reactions. A more reactive element can displace a less reactive element from its compound, forming a salt. For instance, when zinc reacts with hydrochloric acid, it displaces hydrogen because zinc is more reactive than hydrogen. This reaction produces zinc chloride, a salt, and hydrogen gas. In this reaction, zinc displaces the hydrogen in hydrochloric acid because of its higher reactivity compared to hydrogen. Metals like gold and silver are less reactive, which makes them ideal for use in jewelry. Their low reactivity means they are resistant to corrosion and tarnishing, preserving their shine and appearance over time. This property is due to their low position in the reactivity series. Gold, for example, does not react with oxygen or water, which is why it retains its shine and does not rust or tarnish. These metals' resistance to tarnishing and corrosion is why we often see them in applications where durability and longevity are crucial, such as in electronics and jewelry. In summary, the reactivity of metals is intrinsic to understanding their behavior in various chemical reactions and real-world applications. Let's work through some GCSE level questions to apply our understanding of the reactivity of metals in different scenarios. Which metal will react more vigorously with hydrochloric acid, magnesium or iron? Explain why. Okay, so to determine which metal will react more vigorously with hydrochloric acid, we refer to the reactivity series. Magnesium is higher in the reactivity series than iron, indicating it is more reactive. Therefore, magnesium will react more vigorously with hydrochloric acid compared to iron because it is higher on the reactivity series. Let's do another. When zinc is placed in a copper sulphate solution, what will happen? Write the chemical equation for the reaction. To predict the outcome, we consider the reactivity series. Zinc is more reactive than copper, so it will displace copper from its compound. The reaction proceeds as follows. Great, one more. Which metal can be extracted from its ore using carbon, zinc or magnesium? Let's look at the reactivity series. Zinc is less reactive than carbon, so it can be extracted from its ore. Zinc is less reactive, allowing carbon to displace zinc from its compound during the extraction process. Magnesium, being more reactive than carbon, cannot be extracted using this method. By working through these examples, we can see how the reactivity of metals influences their behaviors. In today's lesson, we delved into the reactivity of metals and its crucial role in understanding various chemical changes observed in everyday life. We looked at how more reactive metals rust when they react with oxygen and water in the atmosphere. We also looked at carbon reduction, which allows metals less reactive than carbon to be removed from their ores. We then understood how more reactive elements can displace less reactive ones to form salts. We also understood how low reactivity is useful in jewelry and electronics. Understanding the reactivity series helps us predict and explain various real-world phenomena. This knowledge is incredibly practical, helping us make informed decisions on metal choices in various scenarios.